3.7, the chain rule. We want to go ahead and remember that everything we're doing with derivatives is talking about the changes in y's over how the x's are changing. Remember, we're trying to approach a single point to know what the tangent line or the slope of the tangent line is at that point. Tells us a lot of information. So we use in our notation dy dx. Remember, it's saying the change in y's with respect to x. So what if it becomes we have some kind of function that is not by itself? What if we had, for example, y equals the square root of x squared plus 2? It's really a composite function. If that's the case, then there's two ways our book likes to talk about how to do the chain rule. Version 1 is in this method where we would go ahead and say, well, to find the change in y's with respect to x, we're going to have something where another outside function derivative is going to multiply the derivative of an inside function, or vice versa. So we have something where they have a du going on. So that's our version 1. And then version 2 is saying, well, let's go ahead and definitely use the u substitution where we have some composite function where we're going to say f of u, and then we'll let u equal some maybe g of x. And in this situation, definitely a composite function, and then we're going to take the chain rule using that definition. So our theorem 3.14, the chain rule, we have two versions, using the dy du times du dx, and the composite function, we're saying the derivative of the outside times the derivative of the inside. So let's go ahead and see what we have next. Procedures for doing the chain rule. It says identify the outer function, the inner function, and then you can let u be the g of x. So what they're doing here in two ways, this one's just doing our version 1, you can calculate the product this way. Replacing u back with the g of x where we temporarily had that. This to me seems like a confusing way of remembering it. Remember, I think of it the inside-outside rule. So we want to go ahead, for example, using version 1, given this equation, we're going to use this version. The dy dx is equal to dy du times du dx. And if that's the case, I'm going to say, okay, I'm going to let u be the 3x plus 7, and y equals u to the 10th then. So I'm using the u substitution in here. So then I want to go ahead and take the derivative of this, the du is 3. And then I want to do the dy, sorry, let me change this notation. We'll do du dx, taking the derivative of u with respect to x. And then in this equation, I'm going to take the derivative of y with respect to u. And taking this one, I have 10, using power rule, 10u to the 9th power. So then it's saying, for our equation dy in with dx, dy du times du dx, I'm going to go ahead and replace into my equation what I found here for dy du and du dx. So I've got 10u to the 9th times 3. This is now really 30 times u to the 9th. Last stop is resubstitute in what I found, or I used for the u, which was 3x plus 7 to the 9th. And that is our derivative using the version 1 of the chain rule. Let's go ahead and let's try one that has a version 2. So if we do one with version 2, number 19, given this function, slightly similar to what we just had. We are going to go ahead and I want to, in this case, when I take this derivative, I'm going to do the outside derivative. So inside stays the same, times derivative of the inside, which would be, and I'm going to leave it at this. And that's my answer for that one. Let's go ahead and do another example of this one. This is with a trig function. And we can see it's not simple. We have to do the chain rule here. So when I go to take the derivative of this, I'm going to take the derivative of the outside function, which would be, secant tangent, and we leave the inside function alone. They're being multiplied, and now I'm going to multiply it by the derivative of the inside function, which is 3. So I can go ahead, and rewrite that this derivative is 3 times the secant of 3x plus 1 times tangent of 3x plus 1. And that is my answer of this derivative. Let's talk about calculating derivatives at a point. Given a chart, and I'm going to do number 37 in your book, and they're going to give us a chart that looks like this. So given this chart in 37, they want us to answer a few questions saying, what is the derivative of this function h when we're going to use the value of 3? So basically, given this information, I can rewrite this as a composite function since I don't have a function h in my chart. So they're saying, for example, this is going to be where the derivative of the function f, and using this version of the chain rule. So what I'm going to do is I'm going to say, what is the derivative when g of a is 3? So I'm going to go to my column and see 3 here for my x value. And then going down to the g of x, I see it has a value of 1. So I'm really saying, what is the f prime of 1? So when I go and see an input of 1 on my column here, I'm going to f prime, and its output is 5. So that first multiplication factor is 5. For the second, the g prime of a is 3, so I'm going back to this column here, and I'm looking for the g prime value, which is 20. So when I do that, I see that it actually has a value of 100. If I go to do number B, it's saying h prime of 2, and we're going to use this definition again. That's a composite chain rule. And we're going to do the same process again, that we're going to go ahead and do g of the 2 first. That's this column. Going to the g function is 5. So f prime of 5. And f prime of 5 should be negative 10. And then going to the second factor, I see g of 2, g prime of 2 should be 10. So this is multiplying 10. My value is a negative 100 for this answer. So this was A, then we have B. For example, in this homework problem, it now says for C, what is the P prime of 4? So we're going to use G prime of F of A times the F prime of A. Okay, this was described, these two, H prime and P prime, in the beginning of the problem. And this is what they told us to use. So we're going to go ahead, same process. I'm going to say G prime, but I'm going to value it F4. So given 4, going to the F function, it's 1. f prime of 4. So I'm going to go to 4 and go to f prime. That's -8. Then I'm going to evaluate g prime of 1, going to 1, and then g prime, I see it's 2. So I have 2 times -8, and my value is -16 is for my answer. There are more steps in this problem, but it follows the same procedures. All right, going on, we see that theorem 3.15, the chain rule for power rules. I want to go ahead and say, if g is differentiable for all x in its domain and n is an integer, then it follows this rule. We could do the power rule, and then we have to take it multiplying the derivative of the inside of the power. So let's do an example. Number 41, given this function, so when I want to take its derivative, I'm going to bring down, I'm doing the derivative of the outside, bringing down the power rule, the exponent, and subtracting 1. Now I have to multiply it by the derivative of the inside, which would be 12x to the 5th minus 9x squared. And we're done. So let's do one that seems a little bit trickier. We're going to do number 45. Given this function, this is getting ahead of what I really wanted to do next, which is not just the chain rule once. We may have to repeat it somehow. So if this is the case, for my derivative of this one, I'm going to try to go ahead and still do the same process. Here, and remember, it might be easier to do square roots in exponential form if you don't remember the formula. All right, so here for the derivative of this one, doing the outside function, the square root first. Do the derivative of the square root, leave the inside of it alone. Now we're going to multiply it by doing the derivative of, now this one, remember this one could be rewritten too as cotangent x squared. So I'm going to do that function next. So I'm really going to multiply it by the derivative of this, which would be 2 cotangent x to the first. All right. Then I'm now going to take the derivative of cotangent, and I'm going to multiply it. So that I have now the derivative of cotangent is negative cosecant squared x. So now I've done where I've had to repeat it and do the chain rule twice. So this one technically is the derivative of the outside, the inside, and I multiplied them all through. Just going ahead and kneading this up, I see that these 2's reduce, and I now have a negative cotangent x cosecant squared x over the square root of 1 plus cotangent squared x. And that would be my answer for that one. All right, so then moving on then, I said, we're talking about composite functions of more than one function. So we have here, for example, y equals, this is number 57, x times x plus 1, and then raised to the 5th power. So for this one, it looks like it's a composite of more than one function, but let's see what we can do to start with. Taking the derivative, we're going to do the outside function. All right. Now, I'm going to break it down by saying it's going to multiply the derivative now of the inside. But this derivative of the inside is a quotient. So I'm going to do a quotient rule. I'm going to do my high, my d high, my low, and my d low. And then from here, when I go to write this out, I'm now going to multiply this by x plus 1 minus x over the x plus 1 squared. And then this should all simplify still. So I'm going to keep going. My x's here reduced. I have 1 over the x plus 1 quantity squared. From here, I can go ahead and try to break down. I'm going to go ahead and distribute this exponent here to this one. So I really have 5 times x to the 4th over the quantity of x plus 1 to the 4th power times 1 over x plus 1 squared. And then from here, I've got 5x to the 4th over the quantity of x plus 1 now to the 6th power, and that's my final answer for the derivative. Let's do another example. Number 64. I'm given this function. And here's the reason I really wanted to bring this one in. This one's not that difficult to find the derivative of. The problem becomes in simplifying it in a form that we know is acceptable. So for finding the derivative here, I know I've got the derivative of the first function, leaving the second function alone. Plus, so I'm using the product rule, leaving the first function alone and taking the derivative of the second function. Times the chain rule of this one would be times 2. So let's neaten this up. So now I have this. And I can see from a GCF currently that I could probably pull 2e to the 2x as a GCF. Let's do it this way. 2x minus 7 to the 5th plus 5 times 2x minus 7 to the 4th. And then I can see from in here, this is similar to this, but they're different degrees. So what if I can try to make them similar? So what I'm going to do from here is I'm going to break this down, this first term inside the bracket, as a 2x minus 7 times a 2x minus 7 to the 4th degree. So that I just broke that 5th degree down, plus a 5 times a 2x minus 7 to the 4th degree. Now I can see I have a GCF again. So I can factor out that. So I now have 2e to the 2x times 2x minus 7 to the 4th power, leaving inside the 2x minus 7 plus 5. But then I can see here, this can be simplified. So from here, I'm going to go ahead and simplify it inside of my bracket and get 2x minus 7 plus 5 is really 2x minus 2. I can see I have a GCF again, so I'm going to factor out a 2. So I have 2 times 2, so I now have 4e to the 2x times 2x minus 7 to the 4th power, and then my remainder from the bracket will be x minus 1. And this is my final answer that I'm looking for. Yes, I got that with this derivative, but it's not simplified enough. All right, moving on, we're going to prove the chain rule with a proof. So here's the biggest thing I want to take away from the chain rule is that if we're looking for the derivative of some function h, which we know would be the definition of the limit, and we're going to use not the last definition we had learned, but the one previous to that, as x approaches a, we're going to use h of x minus h of a all over x minus a. So we're going to use this definition in helping us prove the chain rule. So what we want to do from here, though, is if we had a composite function, knowing this, so I really want to say it's the limit is x is approaching a, and we're going to use our composite function. All right, so if this is our composite function, I'm missing a parentheses, how do I go ahead and deal with simplifying this, working out a solution, because right now I can't do direct substitution. So what I'm going to do is I'm going to assume g of a is not equal to g of x. I'm going to assume these are not the same here. And I'm going to go ahead and I'm going to multiply this expression by a g of x minus a g of a over x minus a. And if that's the case, I need to do some other substitution. Let's say v equals g of x, and we're going to say u is equal to g of a, and we're going to substitute that into our equation. So currently, I have this. H prime of a is equal to the limit as x is approaching a. And now substituting these values in for this and this, I've got f of v minus f of u, and it's going to be over v minus u. And then we're going to go ahead and keep our term here. All right. Then from here, I'm going to say this limit here is going to approach to what we would have as x minus a of what we were originally given. And what we're going to do is substitution that we have the derivative of f prime of u times g prime of a, assuming f and g are differentiable. We now have the chain rule.